Hello everyone, my name is Nur Surayahani Suryani, presenting our project entitled Facial Video Based Heart Rate Estimation for Physical Exercise. This video is presented for IEEE Symposium on Industrial Electronics and Applications. This will be the outline of my presentation: background study and introduction of facial video heartbeat analysis, some related works done which related to non-contact photoplethysmography from facial videos, our proposed prototype design of heart rate monitoring system, followed by the facial video heart rate estimation. Finally, the result analysis and conclusion. Heart rate estimation from facial videos is useful in various applications such as telemedicine, public health monitoring, driver assessment, stress management, and effective computing. Human vital signs like heart rate, blood oxygen saturation, and related physiological measures can be measured using a technique called photoplethysmography or PPG. PPG is a simple device which consists of a light source and photodetector for measuring the amount of light transmitted through the or reflected by body tissues. PPG is not only express the heart rate alone, but it can also show some information which related to heart activity. Studies have been done on evaluating remote photoplethysmography signals for heartbeat estimation. Remote photoplethysmography has earned awesome consideration in recent years due to its remote and non-contact features of measuring heart rate. This technique involves optically monitoring light absorption in tissues that are associated with blood volume changes. This will propose an analysis of heart rate measures from facial videos in the presence of heart rate variation for fitness application. The PPG signal refers to the changing light intensity of skin over time. The volumetric change of arterial blood in the PPG signal that is involved in cardiac activity, the changes of blood volume in veins modulates the PPG signals. The PPG signals are composed of two components, DC and AC component, direct and alternating component. The AC component correspond to the variation of blood volume in synchronization with heartbeat pulse, and it is used to measure the heart rate, while for DC is derived from optical signals reflected or sent by tissue. It is determined by the tissue frame as well as the amount of blood in the veins and blood vessels. It shows fractional changes in respiration. So, to perform the AC analysis, the DC must be removed. A small portion of AC needs to be filtered to obtain an accurate PPG signal. The basic frequency of the AC is used to detect heart rate. Remote photoplethysmography is a technique for remote measurement of human cardiac activities by detecting a small pulse-induced variation on the subject's skin, which utilizing a multi-wavelength RGB camera. It measures the variance on the RGB light reflection as the brightness between specular reflection and diffuse reflection. In recent years, researchers have proposed several remote PPG methods for calculating the pulse signals from videos. Contactless PPG method usually utilizes a video camera to capture images, which are then processed by image processing algorithm. The light emitting diode in contact-based PPG methods is replaced with ambient illuminance, and the photodetector is replaced with the video camera. The common image processing steps involved in the framework are region of interest detection, the ROI detection, ROI definition, ROI tracking, and raw signal extraction. In the signal estimation part, a bandpass filter is applied to eliminate undesired frequency component. A common choice for the frequency band is between 0.7 Hz until 4 Hz, which this corresponds to a heart rate between 42 and 240 beats per minute. And then independent component analysis or principal components analysis (PCA) are utilized to separate a signal into uncorrelated components and to reduce dimensionality. In the estimation phase, the dimensionality reduced data will be mapped to the certain levels using frequency analysis or peak detection method. This project proposed to monitor and estimate the heart rate after doing several physical exercise. At the first stage, we designed heart rate monitoring prototype using pulse sensor as an input and Arduino Uno microcontroller. The output of pulse rate will be displayed on the LCD display. Then the next stage is the facial video analysis. The heart rate estimation is performed using non-contact PPG method, while at the same time, previous prototype work has the ground truth. Several image processing steps involved to extract the raw signal from face detection, tracking, and also tracking. Then the PPG signal estimation is done using filtering method. And finally, power spectrum analysis is used to estimate the peak signal for heart rate detection. This is the heart rate monitoring system prototype. This figure shows the schematic design of the prototype using Proteus software. The schematic design of the project system is used to simulate and testing the connection between sensors and Arduino board. At the bottom part, this figure shows how the pulse sensor was placed on fingers and then displayed the heart rate reading value on the LCD display. The dataset used in this work is composed of 80 videos, which accompanied by the corresponding ground truth heart rates of the subjects. There are 20 subjects participated and there are 4 videos were obtained for each of them. The subject was asked to sit on a chair in front of a camera to minimize any movements artifacts during a video recording. The camera was mounted on a tripod and recorded the regions from face of the subject with typical ambient daylight as a source of illumination along with the fluorescent light. These videos were taken with the subjects within 1 meter of skin surface. The heartbeat data were collected in real time using the Arduino and synchronized with the facial videos after doing several exercises. The video sequences have a resolution of 640 times 480 pixels and were captured with a sampling frequency of 20 frames per second. Next is PPG method for heart rate estimation. Python is utilized to automatically identify the coordinates of the phase location in each frame of the video recordings using HA cascade classifier. The ROI or region of interest was separated into 3 RGB channels for red, green, and blue measurement points to form the raw signal separately. After the facial and ROI are detected and able to track it through each frame of videos, the normalized raw traces are combined and fed to the independent components analysis algorithm to decompose it into 3 independent source signals. The independent components analysis used to suppress some of the noise and recover the underlying original pulse signals. Then apply Fourier analysis to estimate the frequency spectrum contents of the time-varying signal. The spectrum of the extracted green channel shows clear spike at the heart rate frequency. The fast Fourier transform FFT is then applied to obtain the power spectrum graph. The FFT will convert the PPG signals from its original time domain to a representation in a frequency domain. The last section is result and analysis. The first graph shows the comparison for both measured heart rate versus the estimated heart rate. Measured heart rate were monitored using the prototype, while the estimated heart rate captured from facial video analysis. This graph shows that the heart rate data for selected 20 subjects under resting conditions. The estimated heartbeat falls within the normal range, which is between 60 to 100 beats per minute. There were large differences in several subjects, which might be due to the lighting and movement effects. The next result shows the graph for measured heart rate versus the estimated heart rate after doing walking exercise. We only demonstrate the static conditions because motion cases requires a lot of attention and factors need to be addressed. The head movement and viewing angle will reflect the focus point of facial skin reflection changes. So therefore become very major difficulty to estimate the heartbeat. And this result shows that the estimated heartbeat falls is expected to increase, which is above 90 beats per minute compared to the body resting conditions. The next graph shows the comparison for after staircase exercise. Subject needs to perform walking upstairs and downstairs for about 5 minutes before the measurement would take place. The stable heart conditions are predicted where the heartbeat will go faster after finishing some physical exercises. We can see that the heartbeat was above 90 beats per minute. In general, the average results for heart rate estimation using facial videos are acceptable and also reasonable to prove efficiency in various conditions of the subject. This table shows good correspondence between the ground truth pulse rate from the heart rate monitoring system prototype and the recovers non-contact PPG for heart rate estimation using ISIEA and FFT power spectrum analysis. The average heartbeat we can see from this table is during resting conditions will fall within the normal range, which is 60 to 100 beats per minute. The estimated heartbeat after several exercises is expected to increase compared with the body resting conditions. And then we can see that the RMSE, root mean square error, and mean absolute error are acceptable, which is below the setting threshold, about 3 beats per minute. So finally, as a conclusion, comparative analysis has been done to extract non-contact PPG from facial video through state-of-the-art algorithm ICA, which was sufficient to estimate heart rate with small relative errors. This suggests the valuability of non-contact heart rate estimation using facial videos under several conditions. So then some improvement can be done on the ROI detection and heart rate estimation process. Further development is needed to be done to extend the prediction for other non-contact physiological state analysis such as respiration rate estimation and also variation of time interval of the heart rate variability. These measures can indicate other indicators such as stress, anxiety, and etc. So, for more general learning algorithm and deep learning techniques can be applied to extract spatiotemporal features and identify the conceivable outcome for advancement in future work. With that, I thank you.